Okay, hi everyone. My name is Kameron Mehling. I'm a fourth year grad student here at CU Boulder, and I'll be presenting this talk called Ultracold Molecules, the Next Generation of Quantum Matter. First of all, I'd like to thank the CU Prime Committee for organizing this talk, giving me instrumental feedback as I made these slides. And I'd like to thank you, the audience members, for actually coming out because every grad student loves to talk about their research. So to begin, I'm going to give you guys a brief history of who I am and my background to becoming a physicist. So this is not really any career goal I ever started out with. If anything, I grew up in a particular part of the US that didn't really prioritize STEM in such a strong manner. So I never really foresaw myself becoming a physicist. On top of this, growing up, the academics or kind of the collegiate future was not something that I was very accustomed to. So the trajectory to becoming a physicist and even a PhD candidate was kind of an arduous one, one that I've really appreciated. And I've had two instrumental factors along this journey. First, the passion for physics. So I developed this actually my junior year of high school after reading this book, A Brief History of Time. And although I don't work in astrophysics, it really was what ignited in me that initial passion. And then also, I have to give a lot of credit to my twin brother, who is also a physicist. This is us on our first day of school, and then this is us on our last first day of school. He is also a physicist here at CU Boulder, and really has been instrumental in me becoming a physicist along this journey. So that journey really started at the University of Chicago when I enrolled and became a physics and math student starting in 2016, and then eventually became a graduate student here at CU Boulder starting in 2020. So to get on with the physics side of this talk, we're going to start with a very basic schema for how we're going to introduce some of the concepts. And I'm going to begin with something known as the boring universe. This is kind of a scheme I've contrived. This box is going to be the confines of our universe, and this ball in the center is going to represent our matter, ultimately whatever we would like to interact with, what we'd like to probe, and what we'd like to understand as physicists. So this is not particularly interesting. You have no unique physics going on here until you make it slightly less boring by adding velocity. So once you have matter with a certain amount of velocity, you can actually start to think about how do you map trajectories, how do you interact with this species, how do you understand or predict novel phenomena from that. And this is really just known as classical mechanics. So I'm going to outline some of these different regimes of physics with these simplistic models. So for all intents and purposes, up until a couple hundred years ago, this was the end of our understanding of modern physics, and my talk would have ended. However, we've gotten quite good at expanding upon our understanding of physics. So as an example, imagine I'm in a universe which is slightly more computationally intensive, one in which instead of just a single ball, I have many balls or many particles in this universe. So this is a new regime of physics. No longer is it entirely constrained only within classical mechanics, but we can think of this as thermodynamics. So you have particles within a box, this universe. They are moving at many different velocities. They can collide. And ultimately, we would like to study the physics associated with this ensemble. And we can think about this as a different regime from the classical mechanics case. Another relevant point to the thermodynamical ensemble is that temperature is ultimately going to affect the dynamics of how these particles within this box will behave with each other. The reason I'm going to highlight temperature is ultimately I'm going to talk to you guys about laser cooling, which is instrumental to all the work we'll do throughout the remainder of this talk. And temperature is kind of the key concept or quantity of interest within that framework. So then from thermodynamics, we can see that if you have a relatively high temperature, your velocities are going to increase. You're going to have a larger spread of these distribution of velocities. And at low temperatures, represented by these relatively thin arrows, we're going to have less momentum, less kinetic energy bouncing around within this ensemble. We're going to go back to this throughout different portions of the talk. And so I kind of want you to keep this in the back of your mind. But to continue along this vein of breaking down different regimes of physics in simplistic terms, we're going to introduce more universes. So this is going to be the discussion portion of my talk, where we can imagine a universe where our particles are moving at really high velocities. We can imagine a universe where my particle is incredibly massive, one where we have more than a single particle, and specifically those particles are going to collide head on. And then also one where the particles have really low temperatures. And what this means is going to be defined through the remainder of my talk. However, for this section, I would like for everyone to discuss what are the different regimes of physics that would be able to be studied with these limitations or constraints. So within a high velocity case, large mass, head-on collisions, or low temperature regimes, you can discuss amongst yourselves if you're familiar with the different physics that's at play here. So everyone doing good? We can go through the answers. Okay, great. So we're going to go through in each of these limits of emergent phenomenon, what physics is at play or what physics emerges in a way that's not typically understood within our classical scheme. So first of all, in the high velocity limit, does anyone want to call out the answer? High energy physics is great. High energy physics relies also on special relativity. So special relativity is going to exemplify itself based on compression of time or compression of matter. Anyone want to call out for the large mass case? Thank you. So that's general relativity. So in this example, you're not actually affecting the matter so much. You're actually affecting the space or the universe around it in the way that you can think about gravity. For these head-on collisions in the bottom left, does anyone know what physics one can study or observe in this example? That's particle physics. So when we think of large particle accelerators, CERN, and the likes, you can think about actually viewing the subatomic constituents of these matter particles when they collide under high energy. So I appreciate that answer. And then does anyone know what physics one can observe in the low temperature regime? Sorry? Condensed matter, we're going to go lower than those temperatures in condensed matter. Quantum mechanics. So that's actually what I study. That's what I work in. So I'm going to illustrate kind of what's unique about temperature and how one can think about making these quantum mechanical behaviors emergent at low temperatures. So in all of these examples, I've shown what physics modifies the situation. And I've drawn this wave here for the quantum mechanics case. And the reason is because fundamentally at very low temperatures, you can see this wave particle duality to matter. And this means that you no longer are limited to thinking about matter simply as a particle or a hard object. You have to think about it as dispersing much like a wave would and interfering with its trajectories or its evolutions. That's a long way of saying that the particle is not actually at any one localized position within the box, but it actually has a distribution, much like a wave would, kind of cresting against the shore. And then beyond that, quantum mechanics also has some other unique properties, namely, I've kind of hidden the rug from you guys in saying that you're constrained within this universe, but quantum mechanics does not care to that degree, and you can actually have the particle outside the box. So this is a little outside the purview of what I'll talk about, but these are some of the interesting phenomena associated with quantum mechanics. This really is what's going to build up a very simplistic view of the universe known as our modern physics textbooks, special relativity, general relativity, particle physics, and quantum mechanics, kind of an experimentalist how-to guide to these different regimes of physics. Ultimately, from now on, we're going to be focusing on quantum mechanics and how we can study new behaviors or new states of matter using the guiding principles. So before I actually dive into the remainder of my talk, I realized that I'm so ingrained in speaking with colleagues that I should give an acronyms guide. So I'll use NIST throughout the duration of this talk. This is actually a scientific facility right down the road. You may have seen this kind of along the Front Range. This is the National Institute of Standards and Technology. We have one here in Boulder, Colorado, and one in Gaithersburg, Maryland. We also have JILA here on CU's campus, which is a joint institute between NIST and CU. This is where I work and my colleagues work on producing these quantum matter samples. LASER is an acronym, which I think some people are familiar with from Jeopardy, but this is something we'll talk about throughout the talk, as laser cooling is going to be the emphasis of how we actually produce these quantum matter objects. And then finally, you'll see YO and KRB, or I may say it throughout this talk. YO is the species of molecules that I work on, and KRB is the species of molecules that my colleagues work on. So hopefully this clears up any confusion that may occur throughout the talk. And if anyone has questions as to something I'm saying that's not clear, feel free to call it out during the remainder of this talk. So to begin with, what the heck is temperature? So I gave an example of a thermodynamic limit, but we're all familiar, this temperature is this little T right here. but the fact that it's at the bottom of this page means we're going to do a little bit of derivation. So to begin with, we can think of something known as a Maxwell-Boltzmann distribution. This distribution tells me for a given mass of a particle and its temperature, along with some other scaling, I can actually predict the distribution of its velocities. This is really instrumental because from a thermodynamic standpoint and ultimately from a laser cooling standpoint, this gives us an idea of where velocities are going to be and how I can relate velocity to temperature. This functional form is closely related to what a form we may be familiar with, which is the Gaussian distribution. This is how you would get graded on a curve within class, or how this is most familiar probably with test scores. And you can actually see that the Gaussian distribution and the Maxwell-Boltzmann distribution have identical functional forms with a couple substitutions. The main one being this 1 over sigma squared, which is the variance, which ultimately tells me how wide my distribution is related to this 1 over t parameter. So in short, what's going to be the kind of defining characteristic of laser cooling is the more I'm able to compress my velocity distribution, the more I'm going to be able to cool an ensemble of matter. And so this will be a little bit more clear in the ensuing slides, but this is a foundational point for the remainder of the talk. This deviates a little bit from the thermodynamical ensemble that we talked about before, where higher temperature just means faster speeds, but they do go hand in hand, just kind of with different emphasis as to the overall kinetic energy versus the width of the distribution. So how we're going to think about this going forward is I'm going to break it down into some rec center physics. So if you guys have been to the UMC, you've seen bowling and ping pong, and ultimately the vast majority of the physics can be explained using this example. So we have a bowling ball, this ping pong ball. We're going to focus exclusively on the forward velocity of this bowling ball, assuming it fits a Maxwell-Boltzmann distribution. So this forward velocity is going to be dependent on its temperature. Now, we don't think about a bowling ball having a temperature in this example, but ultimately the bowling ball is the fill-in for more fundamental units of matter being atoms and molecules. And the bowling ball being so much more massive than this ping pong ball for equivalent velocities is going to have considerably larger amount of momentum. And so what one can think about is if they're on a collision course, as the ping pong ball approaches this bowling ball, we can predict what will happen. They'll bounce off. And so upon bouncing off, we can ask ourselves, what exactly happens to this velocity of the bowling ball? You can discuss quickly amongst yourselves, or someone can call it out. I don't know. That was right. I don't know who said it, but thank you. So effectively, it does not change at all. Almost nothing will happen. And so we're not really interested maybe in individual exchanges of momentum, but the question would be, what would happen if I threw 1,000 ping pong balls at this bowling ball? Now, this is a little contrived of an example, but in that case, thank you, I'll change more. So the momentum of this bowling ball is going to shrink by some corresponding amount by how much the ping pong ball has imparted its momentum to dampen the forward velocity of this bowling ball. Now, this is very much within the vein of classical mechanics. However, this is still just an illustration for ultimately what we'll be thinking about within laser cooling. So if we substitute this bowling ball and this ping pong ball for research physics related concepts, we would have something you could think of as a lithium atom. The reason we're going to highlight this lithium atom is it's a relatively simple atom to think about. It has 3 electrons. And what's most important is you only have a single electron in this outer band. That means that I'll be able to have something known as closed cycling that I'll explain a little bit more coming soon. Beyond just the lithium atom, I'll also have a photon. So the photon in this example is a packet of energy. It's a packet of light. This is maybe outside the purview of what some people are familiar with how we think about light, but really you can just think of it as some infinitesimal ball-like unit of energy. And this unit of energy is going to be colliding with my lithium atom in such a way that if the energy is proportional to the frequency of this laser light, so this omega L term here on the board is going to be the frequency of my laser. It carries some commensurate energy. And if that commensurate energy matches the amount of energy required to excite a excitation within my lithium atom, as an example, then I'll have the ability to actually have these two objects interact. This may not be very clear what that means within the confines of research center physics, so we're going to go back to the bowling ball example. So although the ping pong and the bowling ball do not have these frequencies associated with their energies, assuming I was in a case where the frequencies or the amount of energy associated with the ping pong ball or the bowling ball is not equivalent, as the ping pong ball approaches, it'll actually pass straight through the bowling ball. So there is no scattering in effect. This means that I have to have a particular condition known as resonance for there to be an interaction. So in the case where the two frequencies or the energies between the excitation and my photon are matched, as the ping pong ball in this case approaches the bowling ball, it'll actually bounce off again. So this is saying that there's a way for us to treat quantum mechanical objects in a way that's classical in nature, but it's required a condition where the energies are matched for the excitation and the packet of light. So I want to emphasize that this is all within the confines of a species, an atom, lithium in this example, and this photon, but all the physics will work accordingly in the bowling ball and ping pong ball example. So a secondary mechanism that's really important for us now that we've introduced a way for our light to interact with our species of matter is that we're going to need another way for us to control or tune that interaction based on velocity. So as I mentioned, cooling is going to be dependent on us, our ability to reduce velocity. So we would like to be able to select particular velocity classes to interact with. You may have seen within your introductory physics courses something known as the Doppler shift. This is kind of a still photograph of what that looks like, but a GIF would be as a particle is moving, the way it interacts with these frequencies of light is going to shift whether you're co-propagating or counter-propagating that particle. So ultimately, what it's saying is the way in which the particle interacts with light is dependent upon whether it's moving towards or away from this photon or this frequency of light. In this viewpoint, if I still have this Doppler shift on top of this resonance condition, which I'll put on the board momentarily, for a given velocity distribution, if I'm off resonance, where the energy required to excite my species of matter is not commensurate with the amount of energy within my quantum packet of light, known as a photon, then nothing will happen. It'll pass straight through the lithium atom or the bowling ball in that example. However, if I'm on resonance, accounting for the Doppler shift, which says that I'm actually shifting what is defined as resonance according to a velocity and this scaling factor k, what that means is that I will actually be interacting with my species or the bowling ball only for particular velocities. This gives me a way as an experimentalist to actually talk to particular velocity classes within an experimental setting. And then ultimately, if I'm able to damp the motion of a particular velocity class, so the photons are colliding with my species, then I can ultimately shift the velocities to lower net velocities. And if I can compensate this shift, so what the velocity that's within this purple region, I can actually compress all the velocities near zero. And this is how we're going to define cooling within a quantum mechanical ensemble. So how does one think about compensating for this Doppler shift? So basically, for different velocity classes, how do I maintain this resonance condition where I keep this equal to zero? So first of all, I think as an experimentalist, I can control the amount of energy required to excite a given transition. So if this omega A is the atomic transition for applied magnetic field, I can actually see that I've split my lines to many different spacings than I had before. What this enables me to do is by tuning a magnetic field, I can effectively shift this omega A so that for different velocities, this will still always be zero. This is a way to tune two different components of this relation to maintain the resonance. This could be done experimentally by producing something known as a Zeeman slower, which applies the Zeeman effect as a function of position. So for a laser beam that may be at a fixed frequency, omega L, as I move down the length of this tube, my omega A is changing such that it compensates for the reduction in velocity of the overall ensemble. What this does is keeps all my species within resonance, and I can ultimately slow them to a very narrow distribution at the end of my slowing region. So this blue trace here would be a simulated version of an initial velocity distribution. And then after applying this Zeeman slower, I can compress all these molecules down into a very narrow band near zero velocity. And this is how we define cooling, by this very narrow width of velocities. This is ultimately kind of the key concept, but there's a secondary mechanism that I could apply, which I use within my own lab, which is instead of tuning the omega A, which is the spacing required to excite the transition, I can actually change my laser frequency. And so I don't really have a very illustrative example to show you in this case, but to kind of boil down the numbers, by sweeping my laser frequency, I can decelerate molecules well over 1,000 Gs. So human beings can survive up to 10 Gs. So when you see someone in a rocket ship or on a fighter pilot, they can go up to about 10 Gs. So this is about 100 times faster than humans can survive. And then this is also to say that you can go from 0 to 60 meters per second in 6 milliseconds, which is about 500 times faster than the fastest sports car. So these are just kind of to illustrate how violent and turbulent these mechanisms are, but how efficient one can think about actually compressing these velocity distributions. And then ultimately, at the end of the day, the way that this is done is by scattering about 50,000 of those ping pong balls or photons in that example to ultimately take a molecule or an atom from hundreds of meters per second down to near zero. So hopefully the ideas that stick with you are that we would like to compress our velocity distribution to near zero. And we do this by interacting with the species using laser light through a variety of mechanisms. But when you understand that, you still need to have a place to begin. So to begin with, if I were to have my gas within a box, I would still have background gas colliding and thermally exciting any amount of cooling that I've done. So if I am to reduce the velocity, the background gas within this room would collide with it and ultimately redistribute that thermal energy and actually speed up that gas. So what we're going to need is we're going to need to be in a chamber that has 1 trillion to 100 trillion times lower pressure than the ambient pressure in a room like this. So what that looks like is you'd have a steel chamber that has these holes in them. And these holes are ultimately going to be for our optical access to get our laser beams in so that we can actually interrogate and interact with the matter. What's going through these holes is going to be laser light. And so as an example, this is light that is generated from natural or artificial means. So the lights in this room, the lights from an LED, you can see that it has many different color tones throughout the entirety of its distribution. So it's not very spectrally pure. From a laser standpoint, we can see that that's actually the opposite. So you have a near flat band distribution, except a very high spike of intensity of light or energy at a particular frequency to try to drive these transitions within my species. So this is really kind of the unique aspect of lasers that has revolutionized the ways in which we interact with matter. So if we have these two ingredients, we can think about actually trying to produce these samples of quantum matter by reducing the velocities, confining them within our vacuum chamber, which is this thing here, and interrogating them or interacting with them to produce novel devices. So what that looks like in practice is if you understand that physics, we end with something looking like this. So what this fundamentally is about 1 million strontium atoms confined within a force field made up entirely of magnetic fields and light. And so it's so dense with such a high scattering rate of those photons that you can actually see it with the bare eye. And as a kind of length scale, this is over about 2 inches. So you can see this matter is incredibly dense, at least from a fluorescence standpoint. This is well less denser than physical matter that you interact with in your day-to-day life, but it's getting dense enough for you to be able to actually observe and interact with in a meaningful way. So this is something known as a trap. So leading up to this, we've mostly been talking about how do you compress the velocity distribution, but you'd also not only like to slow down the molecules or atoms, you'd also like to confine them and hold them against gravity for long periods of time. So holding this matter in space is also a tricky game. You're going to use laser lights much in the same way, but instead of trying to damp the velocity, you're going to try to define a position restoring force so that you always maintain within some local minima or some local position within your vacuum chamber. So to mention this, you may be familiar from your first electrostatics class with something known as Earnshaw's theorem. This says that there is no stable equilibrium that you can hold a particle in for a given electrostatic field. So no configuration of magnets, no configuration of E fields that are not varying with time could hold these particles in a stable equilibrium. But ultimately, we don't use static forces. We actually use something known as a magneto-optical trap. So the magneto comes from the fact that we apply magnetic fields that break the symmetry around the center axis. This just really says that we define the location that we would like for this ball of matter to reside. And then the optics is what provides the momentum to restore you to the center of that trap. So the magneto-optical trap is used in labs all across the world and is the basis for all quantum matter experiments, at least within the laser cooling side of things. And so to say this, we now have spatially confined matter that's quite cold. We're getting to sub-millikelvin. And just as a shout out, a millikelvin is about 1,000 times colder than the depths of space, 100,000 times colder than the ambient temperature in this room. This is still just the tip of the iceberg. So from there, we can think about further cooling mechanisms, which are far too many to discuss here. But you can think about if this is the frequency of my laser light on this axis here, interrogating my matter within my chamber, I should get a curve which looks like cooling for some detuning from resonance and heating from some detuning off resonance. This isn't too important that you understand what all those words mean, but what really is critical is to show that I can reproduce this within our lab. And this is something that's done traditionally across all AMO laser cooling experiments, where by tuning a laser frequency, I can get much colder temperatures, and I can observe it in a very predictable and systematic way. From that viewpoint, we're now getting down to 1s to 10s of microkelvin. So now we're getting to 1,000,000 times colder than the depths of space. And this is where you can really start thinking about this as ultra cold matter. Ultra cold being where you no longer can think of it exclusively within a classical regime, but it's the underlying quantum mechanics that actually govern the trajectories and interactions of these particles in this ensemble. So then wrapping up kind of the ideas or the tools within my toolbox, I have something known as an optical dipole trap, which is going to be where I actually deposit the remainder of my molecules or atoms. This is once again built by using laser lights. So if I really tightly focus a high intensity beam, I can see that anything that's caught within the waist of that beam, so within the overlap, is actually going to be trapped. This is much like a tractor beam in a sci-fi movie where you're picking up cows and moving them around. And so how we would do this in practice is you could see from a textbook example, this would be what a cross-section of a laser beam would look like. Very high intensity in the center and then falls off as 1/r². And then within my own laboratory setting, you can see this is what a laser beam would look like when you plot it against its intensity. And so the fact that it has this circular shape will ultimately make a trap where you're deforming the potential energy such that an atom or molecule gets sucked in. So this is fundamentally what's happening, although this is actually kind of the viewpoint you'd have in a laser lab setting. So you can think of this really just as a tractor beam for cold matter. And then by adjusting the intensity of these laser beams, I can change the depth of my trap. And so going on, if this is my trap and I have all these hot and some cold molecules or atoms residing in it, by lowering the depths of this cup or the brim of this cup, I can let the hottest species actually fall out the edges. And what this will do to my velocity distribution is really compress it, which is, once again, cooling my ensemble dramatically. As this ensemble cools, I can think about undergoing a phase transition. So much in the same way that if I cool a vapor, it'll turn into a liquid. If I cool a liquid, it'll turn into a solid. This gas will actually cool to the point where the distribution no longer resembles what would be expected within a classical setting, but actually one that deviates strongly. And this is the emergence of a degenerate gas. So this is quantum matter in a way that cannot be replicated in any setting outside of these vacuum chambers using laser cooling, using evaporation, which is this process here, using dipole trapping forces. So this is really the culmination of everything that I've talked to you about and how one can think about producing these forms of quantum matter. So this has been many years in the making. Everything that I've outlined is going on 30 and 40 years of discovery. So to kind of give out some recognition, the first Nobel Prize in this field of research was awarded in 1997. quickly followed in 2001. So it's picking up steam in terms of the scientific community appreciating the developments. And then most recently in 2012. And the reason I highlight this is I mentioned at the beginning of my talk that I'll reference NIST and JILA quite extensively. And these are the distributions of awards here within our own community. So we have 2 JILA physicists, 1 NIST stationed at Boulder, and then 1 NIST staff scientist stationed in Maryland. So there really is a rich interplay within this field of physics here locally. And a lot of the pioneering work has been done at CU and in the neighboring scientific facilities. So at this point, you could think that I'm at the end of my talk, but I really haven't said anything about molecules specifically. I keep talking about them in a vague sense, but I'll finish off by saying why molecules are the next generation of quantum matter and why I like to focus and hopefully will have my research carried on past. So to begin with, molecules are unique because you have the ability to study chemistry in a way that atoms don't have. So with atoms, you may make a species of cold matter, but it's entirely made up of the same element. So those elements could be lithium, cesium, rubidium. But as they get denser and denser, the collisions or the interactions of these individual particles aren't that interesting because you can only make larger complexes of strontium, lithium, cesium. With molecules, you actually have 2 different constituent particles. And so you can look at how bond lengths will change, how interactions will form, how you can disassociate and form new, more stable pairings. So this gives us a very tunable platform to study cold chemistry, it's what it's called. On top of this, molecules, as we'll show in the ensuing slides, have a lot more internal degrees of freedom. What an internal degree of freedom means is going to be elucidated, but for the time being, you can think about there's just a lot more levels that you have to be worried about where you can think about interacting with this molecule. And then on top of all of this, the molecules break a symmetry plane because you have something known as the internuclear axis. So with an atom, it's spherically symmetric, or the center of the nucleus we can think of as spherically symmetric. So there's no way to break the orientation because any rotation or any revolution is going to be identical. With a molecule, that's not true because you can see you have, in this case, the blue on top and the red on bottom versus the red on top and the blue on bottom. So this defines some level of orientation that's relevant for us to study novel physics. So there's actually 2 pathways for us to produce cold matter with molecules. The first is not actually what I work on day to day, but I'll give a shout out to because my colleagues do. This is using associated molecules. So the idea would be to laser cool species A, then laser cool species B, bring them very close together within a trap, and then you can actually produce a weakly bound molecule. So this is the first cold matter experiments that really were successful. And so you could think of it kind of in this setting where using a camera, I can read out some amount of fluorescence. So I can see the interaction of light with my matter. And I can see a sodium particle with a cesium particle, bring them close together and turn it into sodium cesium, a composite molecule. This has been quite successful. It's done through kind of a transfer process, which is really technical, but the first ever degenerate molecular gas was produced also here at CU in JILA within my own lab, although not on my project, using the KRB experiment, and it was the cover of Science. So kind of interesting for that sake of things, but much of what I work on would be pursuing trying to realize very similar systems, not with associated molecules, but with laser-cooled molecules. So the key distinction is instead of laser cooling the molecule itself, the associated molecules are laser cooling the individual atomic constituents and then producing a molecule from those cold gases. We work, on the other hand, by taking a molecule and trying to apply everything that I've talked about within the realm of laser cooling directly to that molecule. So this would be, once again, the stable trapping condition that I've talked about. And the payout is that you get a lot of new interesting physics to study, but it's quite challenging. So first of all, you're going to have to deal with a lot more internal degrees of freedom. I'm very close to explaining what that means, but the internal degrees of freedom are going to be a huge hang up. On top of this, you're going to need a very large infrastructure to maintain these excitations required to slow, laser cool, and trap these molecules. And ultimately, it's going to be more expensive to produce and maintain all the equipment. on top of the fact that you'll need to develop new laser cooling schemes. So all of this is a mouthful to say that laser cooling molecules is quite challenging. But the benefits to thinking about laser cooling molecules is you're no longer constrained to only making molecules from species of atoms that can be laser cooled themselves. So I can make a molecule that ultra cold that each of the individual atomic constituents have never themselves been laser cooled. So YO, the yttrium and the oxygen that produce the YO molecule that I work with, as far as I'm aware, there's not actually a ultra cold yttrium or an ultra cold oxygen, but there is an ultra cold yttrium oxygen. On top of that, you're going to have the ability to study chemistry with naturally occurring molecules. The associated molecules are molecules that have never existed within the confines of the universe except within a laboratory setting. So they're entirely contrived by experimentalists. And on top of this, by laser cooling the molecules directly, you have all the requisite equipment to probe and interact in a setting that would make these molecules an interesting platform for studying physics, producing devices, making sensors, all the fun things we think about as experimentalists. And then finally, we really want to know how high or how large one can go in thinking about producing these cold gases. So if you can produce a cold gas of 1 atom, who says to stop at 2? You can produce a cold gas of 2, who says not 3? And so by scaling up, you can leverage unique features of each of these different platforms. So the internal degrees of freedom that I keep referencing is related to the fact that you no longer have a symmetry about the atomic species. So you have the Y on the left and the O on the right. And if you undergo a rotation, you can actually swap that order. And this is different than in an atomic case because there would be no way to identify whether an atom had rotated or not. And it's entirely predicated on the fact that you have this internuclear axis binding these two atoms. On top of this, you also have a secondary degree of freedom, which is going to be the vibrational mode. So how far the O and the Y are from each other is able to stretch and ultimately expand or contract as a function of how much energy is within that internal degree of freedom. So these are on very different energy scales. So rotational degrees of freedom in my molecule are typically at tens of gigahertz, while my vibrational degrees of freedom are at tens of terahertz. So that's off by a factor of 1,000. And that means we have different ways of addressing these degrees of freedom. So how I'm able to talk to or transition between one rotational state to a higher lying rotational state, or one vibrational state to a more excited or a lower excited vibrational state is going to depend on the energy spacing. What this looks like in practice is if anyone's played the game pachinko, the idea of the game is you take a ball and you drop it through these pegs and it can land in any one of these buckets. And so these buckets would win you a prize at the carnival. But this is going to be an illustrative example for how we can think about laser cooling molecules and atoms. So if in this example, this ball up here is actually my electron, which is what I'm interacting with to impart my momentum using the laser cooling. I know that it's quite high lying, so it has a relatively large energy from the ground to the excited state. And so from that viewpoint, when it de-excites, it could end up in a lot of different buckets. Now, if I'm working with atoms, fortunately, the number of buckets are quite small. So I wrote cooling and repumping, and I'll show a level structure of rubidium, which would say that I have these transitions that I'll be able to do all my slowing, trapping, and ultimately interacting with the rubidium species with. And this delta E might be very large, but the number of buckets are only 2 that I can fall into. And so I only have to worry about getting my electron out of one of these 2 states, and I'll be able to maintain cycling continuously. The ping pong ball will always bounce off the bowling ball if I have the 2 lasers on this transition and this transition. In the case of molecules, it's not so favorable. Because those internal degrees of freedom are so dense, I actually have maybe a very large cycling bucket and then many smaller buckets off on the periphery. And so what this looks like diagrammatically is if this is the example where the buckets are really large, or one large one with many smaller ones, in the level structure diagram for my molecule, it would look something like this. So this is the added degree of complexity compared to thinking about laser cooling in atomic species. So each one of these lines is something a laser or a microwave would have to talk to, or some level of engineering has to go into to make sure you never occupy any of these levels. And this is what's requisite to think about laser cooling these molecules. So that's kind of the overarching view of why it's challenging. So I'll give you kind of a quick synopsis of some of the work that we've done within my tenure here, and then we can have questions at the end. So when I started, we used to be very big gas. So it wasn't very dense. You weren't able to see it by eye yet. You couldn't really probe it in any way other than with the light itself, which doesn't make for a very interesting platform. Then with time and different compression schemes, you can actually take something that's quite large and compress it very small. So these are all plotted on the same axes, except this one is zoomed in considerably. And what you can see, though, is that the intensity of the fluorescence that I'm collecting, so my ability to pick this out of the background, the ability for me to see it within the lab is quite diminished here. And so this could really boost my signal to noise ratio. But for the first time, we were able to hold it stably within one of those optical dipole traps. Then moving on, we created the first ever MOT mechanism that was able to really enhance the density drastically. So this scale here would be indicative of this amount of density at the initial loading of my trap time. And then as a function of time, I can see I'm really able to compress my molecules to a much higher density. And what this will enable me to do is really boost up how many of my molecules I can load into those optical dipole traps for interrogation. On top of this, you don't need to worry too much about what's happening here, but we were able to cool them to a record temperature. So we have directly cooled molecules down to about 1.5 microkelvin. And this is the cusp of thinking about pushing to degenerate gases. And then where we are today is much like this trap here. We can load into an identical trap, but you have much higher signal to noise ratio than we had before due to this compression and due to the much lower temperatures. So a much higher loading efficiency from the background gas. And then that higher density within this trap leads to us actually observing our molecules colliding with each other. So you're getting to the point where you no longer can think of these as molecules in isolation. So it's not just a gas within a volume, it's a gas within a volume that's starting to bounce off each other. And you can see that here by seeing the loss of my molecules as a function of time. And if I just assume that there was no interactions within the molecules inside the trap, I could not explain the data points here. But if I assume that they are colliding, I can readily explain the loss. So that really is the culmination of my slides and the research work towards ultra-cold molecules here at CU Boulder. But we really have to thank a large number of people for making this a reality. So first of all, I have to thank my advisor, Jun Yi. He's a pioneer within the field of ultra-cold molecules. And also Debbie Jin, who, although I never met her, she passed, unfortunately, before I arrived. Her legacy really carries on within the work that I do and my colleagues carry. Past members of the YO team and the KRB team are too many to name. These are only the members over the past 5 years, and these projects have been going on for almost 15 years now. So quite an immense amount of work. And then the current teams are KRB right now, and then YO today. And then naturally, as any good experimentalist, I have to thank the people that pay the bills to enable me to do all this. So at that point, we can talk about what my day actually looks like experimentally, and how that functions typically is as I work in a laser lab, there's a lot of lasers to be maintained, to be turned on, checked. We don't like to leave everything on while we're gone. You run into potential damage, things overheating, equipment degrading over time. So typically my first hour is going to be checking all my systems, getting those warmed up. The next few hours are going to boil into me looking through potentially new cooling schemes, new trapping schemes, new electronics that I can implement to have better control or interactions of my molecules. The quantum gas or the ultra cold matter is not that interesting in isolation. You have to have something to do with it or to study that makes it unique. And so we're always working on new ways to probe these systems. And then finally, much in the same way in the first hour where I start everything up, before I leave, we'd like to either make slides as a recap of what we've done or shut things down so that we don't catch the lab on fire. So that's kind of the hard and fast way of living as an experimentalist. And then I'd like to thank once again the CU Prime organizers for putting together this talk. And if anyone has questions, we're willing to take those now.
matter down to ultracold temperatures. Could you maybe briefly discuss some of the reasons why this is interesting? Why it had that early applications to ultracold matter?
So kind of inherent to the fact that you have some defined temperature is that temperature in a lot of ways is a very randomized process. And to study quantum mechanics, you'd really like to isolate some subtle features, such as things known as coherences or this wave duality to the matter. And so when you have high temperatures, what that does is it randomizes this noise on top of all these quantum behaviors. So by cooling or removing all this excess temperature, you get rid of the bulk of the fluctuations that allow you to really understand quantum mechanics in its natural setting. Does that answer your question?
So I might be way oversimplifying this, but like, eventually after long enough, when you have the laser on the system of gas, would that, like, how does that not heat it up after? Because you're adding energy. I feel like you're adding energy to the system by having the laser on it.
So you can very easily add energy to the system, and there are some situations where we actually purposefully add energy to study effects, typically after it's been made very cold. You could hold it indefinitely and maintain it at ultra cold temperatures, regardless of how long you have the lasers on. And that boils down to the fact that when we think about lasers kind of in a classical setting, you're addressing many transitions simultaneously. And what's happening is you're actually dumping energy into that ensemble and raising the average kinetic energy of the vibrational modes or the rotational modes.
Yeah.
In the case where you're working with a specific species, so a YO, so the species would be the molecule of interest. So that'd be YO or KRB, cesium, lithium. It's not actually deleterious to apply the laser for that long, as long as you're tuned either the atomic transition or the wavelength or the frequency of that light in such a way that you always are actually removing energy on average. Now, how one removes energy by adding energy seems a little counterintuitive, but the idea is that that energy that you begin with is in that velocity distribution.
Yeah.
So that velocity distribution is actually at very large energies. And even as you really compress that velocity distribution, you have mechanisms that are much more resolved to address velocities that are away from zero and not velocities that are near zero. So as long as you're always addressing velocities greater than zero and pushing towards zero, you will always have cooling. And that's similar to how one can think about the traps. But instead of velocity in that case, it would be space or your x coordinate.
Yeah, I want to make sure I understand, because we're throwing a bunch of ping pong balls at our bowling balls. And it does seem like if the bowling balls are going in all different directions, like on average, that's going to speed up the bowling balls if we're just throwing at them. But I guess you're saying now that most of the pong balls are just going straight through it, and we're tuning it so that only the bowling balls that are going towards you get slowed down.
So
see the ping pong balls.
So I guess there's kind of two aspects to that. To begin with, you define a forward velocity based upon where you produce the vapor of these species, so the cesium, the lithium, the YO, relative to where you're trying to ultimately load them within the trap. So only molecules possessing a certain velocity class will ever even make it down that region. So a molecule or an atom possessing the wrong velocity will just bounce around within a chamber far upstream and will never make it to me. So in some sense, the geometry of the system already confines the forward velocity considerably. On top of that, yes, the bulk of the interactions will just transmit through the species of interest. However, there is so much flux of this gas that you really only need to be able to capture 1% or 0.1% or 0.001% to really build up high enough density to study this quantum matter. So ultimately, you can be terribly inefficient, but just as a raw numbers game, you can still produce this quantum matter. So at the end of the day, there is no assurances that we're being very efficient with the production means, but this is still way less matter than what's inside the chairs we're sitting on or anything that you could physically hold. I mean, we're talking billions of times less atoms. So efficiency is kind of a funny way to think about it in that regime. I think I saw another hand. Yeah.
What's the benefit of using species of molecules rather than like ions and bubbles?
Sorry.
What's the benefit of using like species as molecules rather than say like ionic or related bonds?
So the species of molecule that we use are tailored for in allowing us to laser cool them. The underlying bonds typically are covalent, just as a practical means, but you could use technically any bound molecule as a candidate for doing laser cooling onto it. It's really the laser cooling is reliant on where the electron is. And as long as you have an electron that enables you to excite and de-excite in such a way that you can damp the velocity, independent of whatever the bonding mechanism is, you're allowed to do that. So these molecules for initial work in making these cold gases were chosen 20 years ago almost. And a lot of ongoing work is finding better candidates to make the lives of experimentalists like me a lot easier. But you know, the counter side to that is that we've had a head start of about 10 years, so a decade. And a lot of the initial work is being done here at CU. There's a lab at Harvard, there's a lab at Princeton, one at Chicago that are kind of really working out the kinks. And then as we figure out what's requisite for us to produce these cold matter samples, you can think about choosing a different molecular bonding interaction or a different species altogether that benefits you in one way or the other.
Explain why we that.
Why increasing the density matters to us?
Put these instead of eating eggs.
So that's actually a very fair point. Why increasing the density doesn't lead to heating. So there is thermodynamically a law that says that as I exchange density, I actually will increase my temperature. And so this is kind of related to Pervner in some sense, the PV equals nRT that we learned, I think early on in thermodynamics. The answer is that by applying the lasers constantly, I'm always able to remove more energy or entropy from the system. So although the density may be going up, I have a secondary mechanism that's able to siphon off this excess entropy that may be creeping into the system as I am altering the thermodynamic ensemble. So in isolation, if I were just to change the density, I would have considerable issues. But by applying my lasers on top of changing the density, I'm able to actually dissipate this excess problematic fluctuations in temperature or the thermodynamic entropy. I think we're done with questions unless anyone has a final one. But I appreciate everyone's time.